I start with a little rehash of a keynote given by George Verghese at SIGCOMM. I guess some of you remember, where it was not with these two rivers, so these are Swiss rivers, but he used Missouri and Mississippi. I think he said we are really at the interesting inflection point, and it's a great time to be a scientist. Why? Because computer networks, they're really becoming more flexible, programmable, virtualized. This opens a lot of questions, algorithmic challenges, and opportunities, of course. And today I want to show you some of them, and it's a tutorial, so I want to show you a little bit the algorithmic challenges and problems there also, and some of the techniques that you can apply. So it's about time that computer networks become more flexible. So data center networks, enterprise networks, the internet are really critical infrastructures, and they shifted a lot in scale and applications, obviously. I don't need to tell you. Of course, so initially the internet looked something like this. It was used for file transfer, email, and it was mainly providing connectivity among researchers, universities. Now it more looks like this. I don't know what kind of concert this is, and of course it's very different applications. Live streaming, Internet of Things, quality of service, low latency is becoming important. At the same time, of course, you have also seen this kind of picture. You can do a lot of innovations here on the higher layer of the internet. You can do a lot of innovations also in the MAC layer, in the physical layer, but you couldn't do a lot of innovations at the core, at the internet core for a long time. And one of the promises here of network virtualization is to overcome these ossifications there, okay? And I give you here some examples just in the context of Internet of Things. Of course, you will need a lot of addresses, so it's expected by 2020 you need like 20 billion IP addresses, let's say. And also you heard, of course, about these denial of service attacks coming recently also from these new kind of applications like the Internet of Things. So network virtualization allows you, in principle, the vision is that you can tailor your networks, your stack, and also the protocol stack and the networks to somehow the specific application and the specific routing protocols, addressing scheme, transmission scheme that you need for this kind of applications. A second opportunity here comes from the more flexible deployment and resource sharing that is enabled by network virtualization. So you have a physical infrastructure with networks, routers, servers, and so on. And now with network virtualization, you can deploy very flexibly, and at low cost you can deploy a lot of new services, and you can share these resources more flexibly. So you have different applications, virtualized applications, you can allocate them and embed them flexibly. Of course, this raises the question, first of all, algorithms to allocate this kind of functions, resources, services to the physical infrastructure, and also it raises the challenge how to ensure predictable performance isolation. If you have many applications sharing the resources, of course, you need to take care of isolating them also in terms of performance. And this is mostly the topic I want to look at today from an algorithmic perspective. And of course, the focus will be on the network, because this is a network seminar here. And I don't think I have to repeat a lot of motivation why the network is important. I think we had heard yesterday some enough motivation from Facebook using a high percentage of runtime for the communication. Then systems become more memory-based, so the network is likely to become maybe a bottleneck again. And of course, if you have a communication and you want to have a predictable performance, you need to be able, for example, to reserve bandwidth. And ideally, you want to keep communication local, because if you keep it local, then you kind of reserve less resources there. At the same time, traffic matrices from, for example, data centers in this case. So this is a rack-to-rack communication matrix. I stole this from the Projector paper at SIGCOMM last year. So you see that the traffic matrices are far from random, and they're also quite sparse. So they have a lot of structure that you can exploit in principle. Here you see that between many racks there is little to no traffic here. So this is the white space here is basically the the lack of communication there. So that's a lot of structure. And probably you remember also Ken's talk yesterday where he tried to exploit those structures in changing the network. So if you don't take into account these kind of matrices, then you're kind of forced to either over-provision. If you don't know what is the traffic matrix there, you have to over-provision or you under-provision, and then of course the performance becomes more unpredictable. So mostly I will talk today about allocating functions and allocating bandwidth, but before I do that, I want to show you a little bit that things are a little bit more complicated than just reserving bandwidth. If you want to have predictable performance in network virtualized environments, you need to take care of a lot of aspects and sources of potential interference. And one example I want to show you now, and this is really just a short side track. If you have we set up a very simple example test bed here, where we have 3 switches and then 2 virtual networks here. And these virtual networks are based on SDN, on software-defined networks. And let's assume we have perfect bandwidth reservation here, perfect isolation of the traffic. So in principle, you would say this is a good kind of predictable virtual network because we isolate them from each other. Of course, if you have a network virtualized environment, you most likely, by default, have a hypervisor that takes care, basically, of the translation, message translation. You have heard, I guess, of FlowVisor, OpenVertex. So this kind of hypervisor, network hypervisor, provides the abstraction and translation of the control plane messages. And the hypervisor here, for example, in SDN setting here, it intercepts the packet-in events, then it translates also the flow mode events, and so on. These can include the port numbers, the translation, the switch DPID, and so on. Now, this is also a source of unpredictable performance, unfortunately. So we ran some experiments where, I mean, these are superficial experiments, just to make the point here. So we collocated the hypervisor with a quite noisy neighbor with a high CPU load there. And then we started to load websites, and we measured the latency here if the hypervisor is very highly loaded and if the hypervisor is not highly loaded. And of course, you see the latency actually depends on the hypervisor as well there. You can also see that the performance depends on the hypervisor type. So is it using Nagel's algorithm? Is it multi-threaded? Is it like FlowVisor? Is it OpenVertex? You can also see that it depends actually on the number of tenants, which is highly undesirable, that of course the number of collocated tenants somehow affect your performance. So you really need to take account for all of the potential resources there in your network. If you want to have a predictable performance, then you should take into account also this aspect. Yes?
So can you explain what is the hypervisor? The network is very simple. I mean, all you have to do is divide the
it's a super simple, yeah.
So how many times a second you need to run it?
Yes, so here, this is a bit, I agree that this is not something that we observed in the data center or so, right? This is something we set up just as a motivation here to make the point. So here, of course, also the number of, for example, interactions you want to have with the controller in a SDN network is really something you want to minimize, of course. So if I have a packet-in event here, then if I don't have a rule installed yet, then the controller needs to react. So maybe the tenant wants to decide what to do with this flow. But usually this is like a cache miss, right? So usually you want to have your network very proactively managed. So each time you go to the controller, of course, this is something you want to avoid. But you don't avoid it all the time, and this is what SDN is about. So you do have the controller, and sometimes it needs to react to your events or proactively install. But I totally agree that usually you want to be proactive and not reactive in this case, right? But you do have the hypervisor there, so this is one thing to keep in mind. You can do without hypervisor, and you have different ways of doing hypervisors, but still. Okay, so let's, however, so this was about this. So, but now let's go back to the bandwidth reservation. So Of course, one of the goals here, algorithmic challenges, is to keep traffic local. So of course, this would not be a very good usage of your network resources in the data center if you have mappers of a tenant 1, of a green tenant embedded here, and the reducers at completely at the other side of the data center in a completely different pod. So then you can have predictable performance if you reserve the bandwidth along the path here, but it will cost a lot of resources along the path. So what can you do to improve basically the cost, resource allocation cost in such a setting? Well, they can do two things. Sorry, here this slide is a bit big, that's why it's a bit lagging. One solution we heard yesterday was to adjust the network, right? So one thing you could do is to see, okay, these mappers here, they communicate a lot with the reducers over there. So why not kind of beam the traffic directly over some mirrors via the lasers to the other side? So this is one option. And I think Ken presented yesterday a little bit the algorithmic challenges behind that. Now the alternative, of course, is to re-embed the resources accordingly. So you can also collocate them to the same rack, to the same server, at least to the same pod. And this is called the virtual network embedding problem. How to map? Yes?
So I mean, if you collocate, then aren't there a risk of failure and then everything going down?
Yes, so you have a trade-off there. Of course, collocation also introduces shared fate and so on kind of thing. So that's why I also said not maybe the same server, but maybe the same rack at least, right? Or geographically close. But if you rely on the same hardware, maybe it's okay if they fail together, but it's the opposite goal is to balance here and then make sure you have a fault tolerance. So these are the kind of two objective functions you can have. And I'm not saying this is the better and the other one is the worse, but usually you try to keep communication local. And I want to tell you some of the challenges here categorized in 3 parts. First, about static embeddings. I want to show you a bit some of the challenges there. Then about reconfiguring in an online manner embeddings. What are the algorithmic challenges there? And if time permits, in the end, I will also talk about admission control, online admission control of virtual networks over time while providing approximation guarantees. So here we talk about primal dual online algorithms. And this actually is something we developed also with Moti Medina. Okay, so let's start super simple again. So basically, we have 2 dimensions of flexibility in virtual network embeddings. We can embed, of course, the nodes, the virtual nodes here, the virtual machines or tasks or compute units, and then we can embed the paths. Right, so this is a virtual link connecting this virtual machine, for example, the mapper to the reducer. So we can embed both the endpoints as well as the links. And sometimes this is also called, the virtual network is called the guest graph in theory. And in theoretical literature, also this substrate network is called the host graph. And let's say for now we have unit demand here. So these are unit capacity network links here, and we have unit demand on the other side. And let's say we already found a mapping due to fault tolerance or policies or whatever. We have some mapping that is already made of the virtual machines. Let's say virtual machine 1 is mapped here, virtual machine 2 there. And now the goal is only to allocate the links, the virtual links, to map the virtual links. So let's look at this dimension of the embedding problem, how to map virtual links. What do you suggest how we can map the virtual links? This is simple, right? We already have given the nodes. So in order to minimize the embedding, let's say you want to minimize the allocation cost, a natural idea is to just take the shortest path, maybe from this node here to the endpoint. So VM1 needs to communicate to VM2. So let's take the shortest path here and reserve the bandwidth along that path. Now, let's do a second shortest path between VM3. And let's implement this link 3.4 here along the second shortest path there, because these resources are already consumed now because of unit capacity. So what we get in the greedy algorithm is an allocation of cost 6. Right? So the embedding, in this case, if I do it greedy one after the other, it will pay 6. But when you think about it, there is a better way to do it. You can connect like this, and it will cost 5. So you need to jointly optimize the allocation of the two links. And some of you may probably know that this is a hard problem already. Unfortunately, this is a combinatorial problem that is been studied intensively. You would think that this problem perhaps has been solved a generation ago. It's called the disjoint path problem. But actually, it still puzzles researchers a lot. So there has been a big breakthrough recently. So the problem is NP-hard. So is it clear why I need to jointly optimize the two paths? So on undirected graphs, there's been a lot of literature on feasible allocation of these paths by Robert Sun and Seymour. So they know how to allocate in polynomial time, even linear time, if I remember correctly, these paths jointly, joint optimization. But we still lack algorithms for shortest paths. So there has been at iCalc, I think 2 years ago, this is the best paper of iCalc, there was an algorithm that showed a polynomial time randomized algorithm to compute two shortest paths. But we still lack an algorithm to compute deterministically in polynomial time two shortest paths. So this problem continues to puzzle basically the research community. So it seems that even if the virtual nodes have been mapped, it's still a hard problem to allocate even the physical resources on the links. Okay, so this is kind of bad news. Even allocating routes, unsplittable routes, is kind of a hard problem, right? So what about the other problem? What about mapping the nodes, the virtual nodes, to the physical substrate? So let's kind of ignore the challenge of allocating paths. Let's take a very simple physical network, a line, physical line network here, and let's think about, so here the paths are unique, of course, like in a tree. It's a tree. And how to minimize the allocation cost of embedding this kind of virtual network on the line. Unfortunately, also this problem is hard. It's called, you heard it yesterday very quickly. It's Yes, exactly. So just what is the problem about? So if you would map this node here and this node there, then you would pay all these links. So this is uncapacitated network now. If I would embed it there, I would just pay 2 links, which is better. So if I need to minimize the sum of allocation, so this is minimum linear arrangement problem. So also mapping the nodes is a hard problem in very simple kind of environments. So I don't want to frustrate you too more. I just show you a little bit more what is hard, and then I show you algorithms to solve these kind of problems. So of course, when you think about it, you probably heard about the subgraph isomorphism problem. So this is basically a special instance of graph isomorphism, or it's basically the SIP problem is a special instance of the virtual network embedding problem. Why? So you probably know why the subgraph isomorphism problem is NP-hard, because you can, for example, describe Hamilton cycle problems. So does the graph have a subgraph that is a Hamilton cycle? Or maximum clique problem. Does the graph have a clique of that size? So how do I show now that the virtual network embedding problem is NP-hard based on that? I can just ask, okay, I've given a virtual network with E edges or M edges, so can you find an embedding of cost M? Right, so each link has length 1, so this is kind of a subgraph in this case. Yeah, let's skip that remark. By the way, you can embed sometimes very dense virtual networks even in very sparse physical networks. So this is this remark. Virtual network doesn't have to be a minor of the physical network, but let's skip this. So can we at least formulate a fast mixed integer program for this problem? So that's the backup solution. There have been a lot of mixed integer programs proposed here. So can we at least formulate a very efficient program? So what is an efficient mixed integer program in the first place? We'll get to that. So you know that it takes like a linear objective function, then the set of linear constraints, and then usually you, for example, use a branch and bound or prune solver. And how it works is the following. So you have kind of a search tree where you try to find the optimal solution or feasible solution for the virtual network embedding. And initially at the root, there is no variable set, and at the leaves, all the variables of the mixed integer program have been set. And along the way, you're about to set these variables. And of course, the leaf can be either feasible, infeasible, or maybe optimal. And let's say you already explored this green subtree here. You set all the variables in that subtree, and you found already a feasible solution. The best feasible solution so far, let's say it's at this leaf. And however, we haven't seen the optimal solution yet. Let's say it's at the other leaf over there. And in this kind of framework, so the usual procedure, what you do is at this node, you decide, is it worth exploring solutions of this subtree? And the trick that you do is you basically relax all the binary variables or integer variables at this point. And if the relaxed solution is worse than the feasible solution that you already found so far, then there's no point in exploring that subtree, right? So if you do relaxation, you see you can basically prune that part, and this speeds up the mixed integer program heuristically, right? So the question is, can we find good relaxations of the mixed integer program? Can we find a good formulation of the mixed integer program so we can prune a lot of these subtrees? And how do we formulate the mixed integer program? So we could usually have like binary variables that say, do you map this virtual node to this physical node? Is there this binary variable is v mapped to s. And then we have flow variables. If you have a splittable flow, for example, you say, is the incoming flow along the path equal to the outgoing flow? So these kind of constraints. And then you get this kind of constraints here. We say, OK, if the node v is actually mapped on the source of the logical link, of the virtual link, then the flow that goes out of this should be by plus b larger than the flow that comes in, because this is the source of the virtual link, the source of the flow. And if v is mapped, or if the destination of the virtual link is mapped to v, then we don't care about the flow conservation, because there the flow stops. And if the map binary variable here is 0 and this is also 0, then the flow should be conserved. So here it's larger equal, but this it's a technicality to make sure that this is equal actually in this case. So now what happens if you formulate this mixed integer program like this, and you apply it to this virtual network embedding problem. So you have two virtual nodes, and you want to map it to do physical nodes there. So the kind of results that you get from the relaxation of this mixed integer program is the following: that half of the node will be mapped to this node, half of the virtual node will be mapped also to this node, and then basically perfectly split. And why is the LP, the linear program, actually doing such kind of solutions? Well, the flow then, in this case, according to your constraints, will be 0. So the objective function of minimizing the flows will be perfectly optimized. And of course, this is a very bad relaxation if it comes to pruning, because it doesn't provide you any structure or bounds on pruning the subtrees you explore. So formulating a mixed integer program this way is not working very well. And similar reasons, of course, are there that the integrality gap of randomized rounding approaches can be quite large. And if you remember, I think we had it yesterday quite a bit on that approach. So basically, randomized rounding, you compute a relaxed solution first, and then you decompose the solution into convex combinations of elementary solutions, and then you pick probabilistically or at random some of these elementary solutions to be the integral solution. Even if the flows are unsplittable for now, this technique can actually lead to quite a high integrality gap, or even to a situation where you cannot decompose the relaxed solution into combinations of the integral ones. So let's look at an example here. So now we talk about non-splittable flows, and we want to map the virtual links here to integral kind of unsplittable flows. And let's say this is now the host network, and you want to compute a relaxed embedding of this virtual network onto this physical network. So what the LP, the standard formulation here of multi-commodity flow formulation, mixed integer formulation will do, it will basically map again the nodes in a partial manner to this substrate nodes. And this is a legal solution to the multi-commodity flow problem formulation of the mixed integer program. Okay, so here node I will go to this node, and then half of the link will go there. And the problem is that in this case you cannot decompose even this relaxed solution into integral solutions. So you cannot use it really for randomized rounding, because it turns out that node I needs to be mapped basically to both of them. You cannot decompose it. So this is kind of bad news. So we have NP hardness on mapping the links. We have NP hardness of mapping the nodes. We cannot formulate a good mixed integer program that gives you good relaxations. We cannot basically do randomized rounding sometimes because you have the decomposability issue. So what can we do? So fortunately, in practice, the virtual networks, they look different. They're not always like general graphs, and also the physical network is not necessarily a general graph. So one abstraction that people are working with is the virtual cluster. In the virtual cluster, you have a logical link, and you have the virtual machines are attached to this logical switch there. So it's like an abstraction of a virtual cluster as you would see it physically. And each virtual node has a bandwidth B to that link. And it turns out that this kind of abstractions, you can embed them in polynomial time optimally to the physical network. And I show you quickly one technique, then I show you a generalization of it. So let's say this is our physical network, the host network. And currently we have available on each server, we have available 4 cores, let's say. And if you remember, so basically let's assume that each logical node here, virtual node, consumes 2 cores. So let's assume that each of these virtual nodes consumes 2 cores, and let's assume B is equal to 1. So the bandwidth requirement is 1. And I want to map this virtual network here to this physical network. Does anyone an idea how we could go about this? Okay, so one idea is to do dynamic programming, because this is like a tree, right? So the physical network is a tree, and the servers are basically attached to basically the leaves of the tree. So you can do dynamic programming. You map the virtual nodes to the leaves, and then you see how many nodes do I need to map to which subtree, and I can recursively compute the solution. But actually, the solution I want to show you now even works for any physical network, so it's a bit more general than that. Although this particular one, we could actually do dynamic programming. If you want, I can tell you maybe later how to do dynamic programming. Yes?
But you want disjoint parts from each of the VMs to the...
No, now we have capacities. Sorry for saying this. Now we have capacities on the physical network, and for now we assume we have bandwidth 1. We can do other bandwidth requirements, but it's just for normalization. We do need to do some kind of normalization.
But the switch in the virtual network also has to be mapped?
Now, this is a very good question that I wanted to come to, yes. So first I will show you a solution that we also map the physical switch here, which is like usually done in the literature. And I will show you this is actually not, it actually limits you quite a lot in the number of embeddings you can get. So you should interpret this switch as like abstraction that you implement. But if you want to map it as well, and I think you already see the solution, I guess, in this case, you can basically, so let's say again, we have 2 cores on each virtual node, and then what you can do is first you try all possible locations for the virtual switch, for the logical switch. So these are n possibilities. And then you introduce a super source and a super sink, and you connect at cost 0. You make like a graph abstraction now. You connect the virtual switch to the super sink, and then you connect the super source to all of the servers here. And the cost of these links is also 0. But the capacity signifies, or denotes, basically the number of virtual nodes you can map on these servers. So here, each virtual node requires 2 cores. So here we can map 0, here we can map 1, here we can map 2. and here also 2. So this is kind of the extended graph that we built. And now you can compute on this graph a flow. So here the capacity of this link, we'll set it to 5, the number of virtual nodes. And now we compute the max flow here. These are integral links, so we assume we have integral links here. We can compute the max flow from S to T, and then the allocation indicates where to map the nodes. But this is polynomial time. It can be more efficient on this physical network because it's a tree, but you can do this kind of things in this special network. Things will change quite quickly. Problems become quite quickly hard if the bandwidth here would be different. But if the bandwidth is the same, you can do this. However, this is dynamic programming. I think we can skip it. However, as you already asked, the question is, why do we really map this logical switch to the node in the first place? Because this is just an abstraction, and in practice what it means is that for each of these nodes, the aggregate bandwidth in and out should be B. Right? So we don't have to really map this node here, but we basically want to have this abstraction that each virtual machine can communicate at traffic B. So for example, so that the traffic matrix or the polytope of traffic matrices that are allowed here are exactly the same. So for example, here I can communicate half of a flow from 1 to 2, half of a flow from 1 to 3, and the same here. I can communicate B divided by 2 to 3, B divided by 2 to 2. So what is the embedding cost if I want to embed this kind of network now? So I don't insist of placing the virtual switch to one physical node.
Still can do it.
Yeah, we can still do it. So actually it's related to the VPN conjecture. So if you have a tree, a physical network that is a tree, then you can basically do it's still a tree. You basically can even do the placement of the logical switch, because this is a non-trivial result, but you can basically still place the virtual switch. It doesn't cost you anything. But the number of, basically, the allocation cost can be much lower than if you map the physical switch explicitly. Why is this the case? So let's say we have this star network and we want to embed it on this ring, and let's say the capacity here are 2. And we have a demand of 1 here. So we cannot embed this kind of network on this substrate network, because where do you want to map now the logical switch, right? If you map it here and you also map let's say node number 1 here as well, then the total capacity out of this node is 4, but we actually need 5 because we have 6 nodes in total. We need to communicate to 5 other nodes. Right, so this kind of star network, we cannot embed it in this substrate, even though the capacity is 2, because we need actually 5 total cost, right? So if I map this here, then basically I'm constrained. I cannot map it overall. If I do the hose interpretation, if I don't insist on mapping the logical switch, then I can actually find a solution in this case. So here, this is kind of the traffic matrix I get. So I know that node 1, it can communicate at most at bandwidth B to all of the other nodes. And I can do the following mapping. I map the virtual node to this physical node, this virtual node 2 to this physical node, according to the colors. Now I claim that in this network, if you have capacity constraints, I could not embed the star with the center, but I can actually embed the hose model in general. Why is it possible? So first, I will embed a route as follows here that allows me to communicate from 1 to 2 to 3 and basically to all other nodes as required here by the abstraction. Then I will map the logical links of node number 2. So here the red links we also need to map. And let's say we do a route here, or we allocate a path, the purple path here for the second switch. And then the blue node, we can also map it here, and then accordingly, we still need to implement these logical links here to 4, 5, 6. So we allocate the path from 3 to 4, 5, 6. And so on. And if we continue, we basically get this kind of allocation of the virtual nodes and virtual links. And now the question is, why does this embedding actually work? So why is it now feasible embedding? Again, here we have capacity 2. However, now we allocated basically 5 paths on that physical link. So how is this possible? Now, if you go back to the constraint of the host model, you can see that all the traffic here, according to the host model, it will not exceed capacity 2. So here, this link 5 to 6, it's used by path 1, 5, 2, 5, 3, 6, 4, 6, 5, 6. But if you look at the constraints of the host model, let's set b to 1, you can see that the sum of 1 and 5 and 2 and 5, this is smaller and equal to 1. This is requested by the host model. And the same thing goes for the other 3 paths here, so they also must be together, because they always include node 6, so this will also be smaller or equal to 1. So then the overall capacity here is basically 2, at most 2. So in this case, you can actually embed it, and you lose, in principle, in terms of allocation cost, if you insist on the virtual switch mapping explicitly, which doesn't make sense. Unfortunately, if you do it this way and you have capacities on the network, again, the problem becomes harder, of course. If you want to have this kind of abstraction, if you have general substrate networks, it becomes a harder problem again. Yes?
I mean, when you sort of move from virtual switch abstraction to the one with sort of full mesh, are you assuming that all of the links that are directly connecting will have equal requirement?
So here the requirement is kind of a host type of requirement. I know that the bandwidth coming out or going to this node 1 in total will be b. But I can do all to you and 0 to your neighbors, or I can do half to you, half to your neighbor. So this is up to me, basically. But I need to implement it along the physical network.
No, I'm saying, is it sort of always fixed after you have decided, or can it change that?
The route is then fixed in this case. Yeah, there are 2 options here.
Yeah, because in the worst case, when 5 are there, if everyone decides to talk through that.
Right, so there are 2 flavors here, exactly. 2 flavors here, again, of the problem, indeed. So here the assumption is it's fixed in this case. Okay, good. So this was general virtual network embedding. So let's quickly check the time. So now, of course, similar problems arise in different contexts, and probably have heard of, for example, service chains. So this is a new abstraction, service abstraction, where you have a certain flow that needs to go from S to T, and then it needs to traverse certain functions. So for example, it first needs to go through a cache, and then a firewall, and then some kind of optimizer or tunnel entry point or something like this. And the flows need to traverse this in a certain order. And again, similar like algorithms and techniques and hardness results that we had before, we can also apply it here. But it does change things a little bit, and I will show you quickly why and what kind of techniques you can still use. So what is the new interesting aspect here? So originally, or traditionally, if you have a flow from S to T, for example, you go along shortest paths, or at least you go along paths. But now with these waypoints, so these are called waypoints or virtual network functions or middle boxes, now the paths become more complicated because it's no longer a single path, but you need to go somewhere. And in this case, the route will actually be a walk because it's no longer a simple kind of path, but you need to go somewhere and then you need to go back from there. So the paths are actually becoming walks. And again, we face similar problems. So here, in this case, let's assume again that the endpoints are kind of given, and even the network function that you need to traverse, the waypoint, is also given. So how can I find now a shortest path through this waypoint from S to T? Again, if you do it greedy, you will fail, because now you block your resources and you have a long way to go. So you need to do joint optimization. But now it's a little bit simpler than 2 disjoint paths, because one endpoint is basically shared. All right, so in this case, you can actually do a solution of 6. I think this is optimal. Oh, sorry, this is of course not optimal. So you can do it. Okay, I think I forgot. Okay, this was 8. So here you can do 6, but I guess you can do even better.
They do 4.
Yeah, of course. So here, it turns out that the question is it still as hard as computing 2 disjoint paths? And it's actually It depends a little bit, but to some extent, yes. Because even if you have to route through a single waypoint, it's kind of an NP-hard problem. Why? We can make a reduction from two disjoint paths again. So let's assume capacities are 1. Now, if you want to compute two shortest paths, we reduce it to computing a path from S1 to T2 through some waypoint that we introduce, and we connect the waypoint directed link here from T1, the end of the first flow, to the waypoint, and then we connect it to S2 where the second flow starts. So now if you compute the shortest path through this waypoint, it kind of implies two shortest paths, one from S1 to T1 and then from S2 to T2. So you can make a reduction like this, and you see that the problem is still NP-hard, even routing for a single waypoint, if it's a directed graph, because the problem is not NP-hard in undirected graphs. So what happens if you have an undirected network? So in this case, of course, you can reduce it to undirected graphs, because we know that computing two disjoint paths on undirected graphs is actually feasible. So then you can, of course, just compute, in order to compute the shortest path from S to W to T, you can compute the shortest path from S to W and from W to T. So you can do this, and we know that on undirected graphs it's feasible. It's not super fast, but at least it's feasible. But you can do faster in practice. And some of you probably know Surballe's algorithm. So this is a classic algorithm that computes between 2 points, two disjoint paths, edge disjoint paths or vertex disjoint paths. And you can use this algorithm also to compute routes for a single waypoint. And does anyone have an idea how we could actually use Surballe algorithm that computes two edge disjoint paths from S to T to actually compute a route through the waypoint, the shortest route through the waypoint? So you can do the following trick. So you then, you want to compute the shortest path from S over W to T. And now you make again an extended graph construction. So you introduce a super source, a super sink, and then you make basically two connections, one to the source and one to destination. And then you connect the waypoint to the destination. Now you ask Surballe, can you provide me with an edge disjoint path from basically S plus to T plus? And it will compute you here edge disjoint paths, and you can interpret them as the paths from S to W and from W to T. So you can use this algorithm to compute that. There are some caveats that I put under the rug. So first, the Surballe algorithm is used for directed networks, and I described it for undirected, but you can use the kind of gadgets here to make it work. And the classic algorithm was vertex disjoint, and then there was a later one that is edge disjoint, and we need the edge disjoint here.
You mean a bus from one vertex to another that goes to a third vertex?
So these are, you mean the original algorithm was for...
This is what you said, right?
Yeah, so here I compute path, two disjoint, edge disjoint paths from S plus to T plus.
So you get a path from S to T that goes to W.
Yes, because here I only made connections. The only way to reach T plus is via the waypoint.
For directed graph, this is incomplete.
No.
Yes.
He said for directed graph.
This you said this is for directed graphs?
Directed graph, this is an incomplete formula. If you ask if you have a path from A to B via C, it's an incomplete formula.
Let's revisit that, because there is some. I totally trust you. We need to see. I think for let's say assume this is for undirected. There are some caveats here. Indeed, I believe it's probably right what you say. But you may, for example, think, this is great, so we can also use it to compute two disjoint paths, for example, right? So why don't I use this nice Surballe algorithm to efficiently compute two disjoint paths? You can say, okay, let's also introduce maybe if you have a S1, T1, S2, T2, we can also make such a construction and then connect basically through a helper node to the destination. But the problem of computing two shortest paths where you can select the destinations. So the destinations are not S1 to T1 and S2 to T2, but I can also choose S1 to T2 and S2 to T1. This problem is much, much simpler. So this is a simpler problem, but I see what you're saying. Okay, other questions on this? Let's double check that directed part, but I'm not 100% sure it's NP hard there. Do you remember?
So, I mean, maybe confusion is here that now you solve it for undirected graphs. Usually the NP hardness was for directed graphs. When you use the subvalid to say you want to have like this waypoint problem in undirected graphs, and previously it was directed.
So you want to apply, so you want to solve two disjoint paths.
Two disjoint paths?
Yeah, between S and T on directed graphs.
This isn't complete.
Okay, let's take this offline. We need to check that.
What?
No, I mean between same source and same destination, right?
No, that's so.
Not if you allow.
Okay, good. Then I agree, of course.
Allow what you say it's slow.
Yes. Okay, so how much time do we have? I think 15 minutes. 15 minutes. Okay, so let's move a little bit into dynamic embeddings here. So there are many reasons why actually traffic patterns change over time. In particular, arriving new kind of jobs, tasks, and so on. There's also some motivation here, of course, from the Projector paper, where they say you have a lot of elephant flows in the data center, and then you cannot accommodate all of them at the same time. So you need to switch sometimes among them. Of course, bandwidth can change. Streaming applications rate changes over time. So now how to adapt the virtual network embedding so to reflect basically the changes in the traffic matrix. Okay, so again, one approach is to adjust the network over time. Second approach, of course, that we do here is again to change the embedding over time. And let's make it very simple. Let's say we have a rack. We only want to optimize within a rack. We have a single switch and we have a couple of servers. And let's say we have this communication pattern at time t. And now we want to distribute it, let's say, across 4 servers. And let's say they have size 4, so this is kind of a graph partitioning problem, of course, so this is well studied. For example, of course, I want to maximize the communication inside a rack or inside a server, and then I want to, basically, I need to have the same size, because each server can accommodate, let's say, 4 virtual machines. So this is kind of a hard partitioning problem, but now it gets harder because we want to change it over time. So let's say that at time t+1, at the end of the day, maybe you have more communication between node 1 and 3, and also between 3 and 4, and also between 2 and 5. You start to communicate here. Now this kind of embedding you had at some point is no longer really a good allocation, so you need to reconfigure over time. So for example, you want to move node 1 to this cluster, and then basically you move 5 to the cluster with node 2, because now it started communicating there. And let's make it simple for the tutorial. Let's assume that we have inter-server communication costs 1. So each time you communicate across the boundaries, you pay 1 unit. As long as you communicate inside the cluster, you pay 0. And as soon as you need to swap to virtual machines, you will pay alpha, let's say some parameter alpha, which ideally is, of course, larger than 1. And the approach we're taking here is competitive analysis, online algorithms. So you want to kind of minimize the competitive ratio, the cost of the online algorithm that doesn't see the future requests or doesn't know the distribution of the communication pattern, to the cost of optimal algorithm that knows basically the sequence ahead of time. So why studying competitive analysis? I don't think I need to motivate so much here. Of course, if you have a good competitive ratio, an algorithm that gives you a very low competitive ratio, then you don't even have to worry about prediction models or trying to make statistics about your traffic patterns and so on. It just works. Whatever comes, it will basically work just fine. So this is nice about this. And you can think of different settings. So one, which we could call weak adversary setting, is that you just have a distribution that is given but unknown to the online algorithm. But let's say the communication pattern doesn't change over time, the distribution doesn't change, but the requests or communication pattern is sampled uniformly at random out of this distribution D, IID. And the more general or challenging setting is where the adversary can actually choose the sequence completely. So it can set up the communication sequence entirely. And the challenges here, of course, is that we don't know, as an algorithm, necessarily the communication pattern D, the distribution D. And against the strong adversary, we don't know the sequence of requests over time either. And the challenge is here now, you get these communication patterns, you get to see one after the other some of these communication patterns. You learn about the distribution. And now you need to decide. Now I communicated with Musharraf, so this will cost me 1. Will I move directly to the neighboring seat of Musharraf? No. Maybe let's wait a little bit longer. It's kind of a rent or buy problem because migrating there costs alpha. Going there directly, it will be too costly. But if I see over time that the communication will increase, and at some point I just have to go there, because otherwise I will not be competitive against the optimal offline algorithm. And then, of course, if I decide to migrate, we need to decide, will the other server come to my place or will I go to his place? Or will we both go to a completely different server and evict some of the nodes there? And who do we evict on that destination server? So these are kind of the challenges here. Is that, let's say the servers have size 2, then this becomes kind of an online matching problem, right? Because you can just fit 2 servers on there. Unfortunately, it turns out that the problem is quite hard to approximate in an online fashion. And why is this the case? So let's assume we have the strong adversary. And we even give the online algorithm extra capacity. We have some augmented servers where the offline algorithm we can use basically just the servers themselves, 3 slots. And in our case, so let's say the size here is k. And we are allowed, the online algorithm is allowed to use all basically the extra space here of servers of size 2k minus 1. So you could, for example, put all the virtual nodes on one server except for 1. So you can really play with the structure here. And nevertheless, it turns out it's very hard to be competitive against optimal offline algorithm because there is always one edge here that crosses the boundary still. So even with augmentation, there must be one node on the other server. So I can always ask this kind of request. And each time, basically, with each request, the online algorithm has to pay 1 unit. Right? So with each request, we have 1 unit. So what can the offline algorithm do? If you use some kind of counting argument, so interestingly here, this strategy of hitting the online algorithm with each request, it's somehow not depending in any way on the strategy of the offline algorithm. It just depends on the strategy of the online algorithm. So by the pigeonhole principle, or just taking an averaging argument, since there are like many, many different configurations that the offline algorithm can take, so in this case it will be k many, I don't go into too many details, that the offline algorithm in the perfect position, he can go there once and stay there to the minimal kind of location, and it will just pay 1 kth, like 1 over the size of the server at this position. So this is kind of the example where the competitive ratio, the lower bound is at least k, because the online will be hit each time, and I can go to the average, the lowest kind of configuration, and will only be paying at most once every k requests. So even with a very big augmentation, it's very hard to be competitive here. I can, yes?
So, if you're talking about reconfigurable networks, if the physical network can be arbitrarily reconfigured.
Yeah. The physical topology, you mean, yeah?
Yes. So, should we focus on changing the link embeddings as opposed to migrating the nodes?
So this is a very good question. So here I totally focus on a fixed topology for now. But you are asking what is better, migrating nodes or adjusting the network?
And I'm suggesting that migrating nodes doesn't really, I would say, doesn't make sense, but it is not really helpful because you can actually configure the physical network after, suppose.
Well, this is like future music, right? This reconfiguring topologies to some extent. I totally agree that migration is kind of a costly operation often, which should be avoided as good as you can. The question is, what is a virtual node here, right? Is it a big virtual machine? Is it what is really a node in this context? So I kept it quite abstract. If it's a compute unit without a lot of attached memory and disk and so on, so this can be migrated. I guess a task can be migrated quite quickly depending on the setting.
But the point I'm making is migration of VN nodes is somehow equivalent to not migrating them but changing the physical.
Yeah. You can emulate each of them mutually. I totally agree. Yes. But there are limitations on which you can reconfigure your network today, of course. Yeah?
So the lower bound you showed, does that also hold for randomized algorithms?
No, unfortunately not. Yes.
It looks like a paging lower bound. So
yeah, it's a very good point. So this is actually what surprised us here, that with paging, basically, they have this k lower bound for paging. So if you have a cache of size k, then you get a k lower bound for paging. Now there is in the classic paper by Tarian and Slater on online paging, there was also this lower bound of k, but then they show if you have a little bit of augmentation, if you have like constant augmentation factor, then basically the competitive ratio will be constant as well. But in this case, what is nice is that even with a lot of augmentation, you keep the k lower bound. I mean, it's not nice for the algorithm designer. It's not because we are bad professors, but it's just like inherently lower bound.
But it's possible that randomization can overcome that.
Yes, exactly. And then randomized algorithm depends what is, again, your adversary. Is it oblivious? Is it adaptive? These kind of things matter, but it doesn't apply to randomized. I totally agree. And actually, this lower bound even holds if you have requests that are like circular only. You don't even have to have requests between all pairs of nodes. You can have them along a ring. It's already this lower bound. So basically, to some extent, the randomized algorithm that I showed you, or the adversary that chooses the distribution and then uniformly at random kind of picks the request from that distribution, we can show in this case the competitive ratio will be better. So there we can actually achieve a competitive ratio of log n. In this case, under, again, some assumptions on the traffic pattern. Yes, but this I agree. And I think even in the online paging, the relationship to online paging is actually not so immediate as one might think. So first we thought this is kind of a generalization. And there I think the competitive ratio is log k in online paging, but I don't know what it is here. We haven't studied that. So I have like 3 more minutes. I can give you a very quick idea of a simple bound, how you can get it, and then I think we wrap up the tutorial. So here and this algorithm, the technique, I show you here a very bad upper bound, kind of, it's n squared, so it's not so exciting, right? An upper bound of k is actually not so bad in practice because the number of nodes you can collocate on a server is kind of small usually. It's nice, it doesn't depend on time, it's nice, it doesn't depend on the number of servers, but here the algorithmic techniques is similar for a better bound we can prove with a little bit of augmentation. But here I will just show you the bad bound for time constraints. So basically the idea is that we grow somehow a component, so the algorithm cycles through phases, and we monitor each time the online algorithm pays a request across the servers, we indicate it with the edge in this growing component graph. So first we have an empty graph here, so we have the allocation here, and then each time the online algorithm has to pay for an inter-server request, we will add a link here in the component graph. And once the size of the communication here reaches a certain threshold, alpha, we will indicate the edge completely there. We say this is now a stable edge. And on this occasion, we will rebalance all the nodes. We will reshuffle all the allocations of the virtual nodes. This will be very costly to the servers. So this will cost us in the order of alpha times n reconfiguration costs. So each time we have an edge that has been asked alpha times, we will reconfigure once we reach a configuration where we cannot rebalance the components that have been communicating at least alpha times, then we stop the phase. So if we cannot rebalance them in a way that no alpha edge is crossing the server boundaries, at this point we say this, the phase ends, and that's where we do the competitive ratio on, based on this phase. And the idea is, of course, that the alpha edges here in the component, they will form a tree. So the alpha edges in general will form a forest, because once I communicated alpha across a path, these nodes will no longer have the chance to increase their edge weight to alpha, because from then on they will always be on the same server, according to the algorithm construction. And of course we pay a lot for reconfiguring, but it can be easy to see that at the end of the phase, the offline algorithm also had to pay at least alpha. So the communication cost we have per phase is alpha times n squared. And the reconfiguration cost is also in the order of alpha times n squared. And the offline algorithm, it has at least cost alpha, because if he migrates one time, he already has alpha. And by the definition of the end of the phase, the components don't fit into servers perfectly anymore. So there also is one alpha edge that crosses the boundaries. So this is roughly the idea here. And again, there are weaker models where you can get better bounds, and this gives hope that in practice actually this problem can be solved more efficiently, but I think at this point let's stop here. So let's wrap up. For predictable performance in virtualized environments, you need some kind of resource reservation, especially the network. You want to keep communicating nodes together. So we talked a lot about the hardness of some of these embeddings in the static scenario. I showed you some first ideas on how you can do reconfigurations, not by changing the topology, but really by moving around the nodes. And finally, one remark on that, you can also have guarantees over time. If you have a static algorithm that embeds the virtual network up to a certain approximation factor, then you can use on top the primal dual kind of competitive analysis framework from Buchbinder and Nauer, and also get a competitive ratio over time. So if you have a perfect embedding algorithm and you get a competitive ratio out of the online dual primal dual framework that is R, and your approximation algorithm for this perfect embedding is say rho, then you can also get a guarantee over time of R times rho, something like this. Okay, any questions? Yes?
So this is on the part that you skipped. So if you know that you're in the reconfiguration problem, if you know that you're into the coming from a distribution, right? I guess firstly, whether you know the distribution or not is not so important. You can learn it very quickly. Right?
That's already one challenge, actually. Yeah? So let's say you have one node that has a very different probability, and so the starting node, let's say, is a very bad node. And all the other nodes have like roughly the same probability, then it will be bad to wait at this node to learn the distribution with high probability and then move to the node that has the best. So this kind of strategy will not work because you wait too long in the bad, because you pay each time you change your estimation.
Truncate the distribution at some inverse polynomial value and everything smaller probability.
Yeah, yes. So that's one strategy to do exactly. Yes, you can estimate it pretty well.
And then if you know the distribution, can you get a better
Yeah. If you know the distribution well, you can basically move there very quickly. That's the offline algorithm, what it's doing. So it kind of takes a trade-off, how far is it away, the optimal configuration, and then how good is the basically distribution at this place, and then I make the rent or buy basically to go there, yeah.
So that someone suggests that maybe there's a good randomized algorithm because that's the goal of the randomized algorithm.
Okay.
I mean, just like
yeah, you're saying this kind of context, it's possible to have like constant competitive. Okay, cool. If you have a pointer on that, that would be actually nice. Yes. We didn't get to constant competitive ratio on this model yet, yes. But I know that like waiting to learn the kind of distribution is already taking too long in general. Yeah.
The point is that you don't need to learn all the distribution. The moment that you learn some part, you need to start moving toward that.
Right. So we should propagate, and there's really small probabilities it doesn't really matter.
Any other questions? So let's thank Stefan for the nice tutorial.